Ray tracing. Ray tracing is a graphics rendering technique that simulates how light behaves in the real world. Instead of simply calculating lighting with shortcuts, it traces the path of individual rays of light as they bounce off surfaces. This allows reflections, shadows, and lighting to look far more realistic than traditional methods. It stands out for creating cinematic visual quality in modern games. It matters because it brings video game graphics closer to the realism seen in films and high-end visual effects. DLSS, Deep Learning, Supersampling is an AI-powered technology developed by NVIDIA to boost game performance while maintaining image quality. It renders the game at a lower resolution and then uses artificial intelligence to upscale the image to a higher resolution. This significantly increases frame rates without heavily sacrificing visual clarity. What makes it different is the use of neural networks trained on supercomputers. It matters because it allows gamers to enjoy demanding graphics features like ray tracing while keeping smooth performance. Frame generation. Frame generation is a technology that creates entirely new frames between existing ones using AI or motion data. Instead of rendering every frame traditionally, the GPU predicts the next frame and inserts it between real frames. This can dramatically increase the displayed frame rate, sometimes doubling it. Its key difference is that it generates frames rather than simply rendering them faster. It matters because it helps deliver ultra-smooth gameplay even in extremely demanding titles. VRAM, Video Random Access Memory, is the dedicated memory used by a graphics card to store textures, frame buffers, and other graphical data. Unlike System RAM, VRAM is optimized for handling massive amounts of visual information at very high speed. Larger VRAM capacity allows games to load higher resolution textures and complex assets. It stands out as a critical component for high-resolution gaming such as 4K. It matters because insufficient VRAM can cause stuttering, slow loading, or reduced graphical quality. FSR Fidelity. FX Super Resolution is AMD's alternative to AI upscaling technologies. Like DLSS, it increases performance by rendering games at a lower resolution and then reconstructing a higher resolution image. The main difference is that FSR works on a wider range of graphics cards, including many older GPUs. It stands out for being open and accessible across multiple hardware platforms. It matters because it helps players gain higher frame rates even without the newest graphics hardware. G-Sync. G-Sync is a display synchronization technology developed by NVIDIA. It synchronizes the refresh rate of a monitor with the frame rate produced by the GPU. This prevents visual artifacts such as screen tearing and stuttering. It stands out because it uses dedicated hardware modules inside compatible monitors. It matters because it delivers smoother gameplay and more consistent visual performance. FreeSync. FreeSync is AMD's alternative to G-Sync, designed to achieve the same goal of adaptive refresh rate synchronization. It aligns the monitor's refresh rate with the GPU's frame output to eliminate tearing and reduce stutter. The main difference is that FreeSync is based on open standards and does not require expensive hardware modules. It stands out for being widely supported across many monitors. It matters because it allows smoother gameplay at a lower cost. Path tracing. Path tracing is an advanced evolution of ray tracing that simulates nearly every light interaction in a scene. Instead of calculating only some rays, it traces thousands of light paths for extremely accurate global illumination. This produces incredibly realistic lighting, reflections, and shadows across entire environments. Its key difference is its extreme realism compared to standard ray tracing. It matters because it represents the future of real-time graphics, although it currently requires very powerful GPUs. Shaders. Shaders are small programs that run on the GPU to calculate how pixels and objects should appear on screen. They determine lighting effects, colors, shadows, textures, and reflections. There are different types, including vertex shaders, pixel shaders, and compute shaders. Their key difference is that they give developers direct control over how graphics are processed. They matter because nearly every modern visual effect in games depends on shader calculations. Anti-Aliasing. Anti-aliasing is a technique used to reduce jagged edges on objects in digital images. Without it, diagonal lines and curves can appear rough or pixelated due to limited resolution. Anti-aliasing smooths these edges by blending colors between pixels. Various methods exist, such as MSAA, FXAA, and TAA. It stands out for improving visual smoothness in games and 3D graphics. It matters because it greatly enhances image quality, especially on large screens or high-resolution displays. Anisotropic filtering. Anisotropic filtering improves the clarity of textures viewed at sharp angles. Without it, textures such as roads or floors can appear blurry when viewed from a distance. This technique preserves detail by sampling textures more intelligently. Its key difference is that it focuses specifically on texture sharpness rather than edges. It matters because it makes environments look clearer and more realistic, especially in open-world games. Display sync. Display synchronization refers to the broader concept of matching frame output from the GPU with the refresh cycle of a display. Traditional methods such as VSync attempt to lock the frame rate to the monitor's refresh rate to avoid tearing. However, this can sometimes introduce input lag. Modern adaptive sync technologies like G-Sync and FreeSync improve this process by dynamically adjusting refresh rates. It matters because proper synchronization greatly improves visual stability during gameplay. Rasterization. Rasterization is the traditional method used by GPUs to render 3D graphics in real time. It works by converting 3D objects made of polygons into a 2D image made of pixels that can be displayed on the screen. During this process, the GPU determines which pixels belong to each triangle and then applies textures, colors, and lighting using shaders. Its key difference is that it focuses on speed and efficiency rather than physically accurate lighting like ray tracing. It stands out as the foundation of real-time graphics used in most games for decades. It matters because nearly every modern game still relies on rasterization as the primary rendering technique, even when advanced features like ray tracing are enabled. Texture filtering. Texture filtering is a technique used by GPUs to determine how textures appear when applied to 3D surfaces. When a texture is stretched or viewed from different distances, the GPU must decide how to sample the texture pixels. Basic filtering methods can make textures appear blocky or blurry. More advanced filtering improves smoothness and detail across surfaces. It stands out because it helps maintain visual consistency in complex scenes. It matters because nearly every object in a 3D game relies on texture filtering for proper visual quality. If this video helped you understand GPU features better, don't forget to subscribe and click on this other video for more explanations on another topic. Thanks for watching and see you next time for a new video.